Hello my dear students. Today's topic is self-induction. Now, we already know what is induction. With a change of magnetic flux, an induced EMF and induced current is generated, and that induced current or EMF is known as induced induction, process of induction. Now, when a current flows through a coil, it produces magnetic field around it, and hence the magnetic flux which is linked with the coil. If the current through the coil is changed, the flux linked with the coil also changes. So this is the coil. When the current starts moving, it generates magnetic field, and magnetic flux is magnetic field per unit area that starts being originated when we change the current. Now there is a rheostat in this circuit. When we make it over here, that means we are including the very less part of the rheostat, so resistance is very less, so current will be increasing, okay, because that is a function of the rheostat. In this diagram, the main current, the current which is being generated by this battery, increases as we make the resistance minimum. Therefore, an induced EMF is set up in the coil and induced current flows through it. Now, with the main current, what happens? First, the main current will start flowing, which is I. With the main current, when current starts flowing through a solenoid, what happens? Magnetic field will be generated, and with the induction of magnetic field, when magnetic field starts generating, magnetic flux will be created. With that, induced current will also be generated. So there are two types of current in one same circuit. One is the main current given by the battery. Another one is the induced current generated by the magnetic flux or change in magnetic flux. Now, according to Lenz's law, the induced current always opposes the change in the main current. So what we know is, when the induced current is generated, that induced current will always oppose the main cause which is giving the magnetic flux or which is giving the induced current. So this main current is giving the magnetic flux, so the induced current is so generated that it will try to stop the main current. It will oppose the flow of main current. So if this is the direction of main current, induced current will be generated in this particular direction. So this is the direction of induced current. So when the current starts increasing, magnetic field is generated. Magnetic field, when it is generated, magnetic flux will be originated from every loop of this solenoid, and with the change in magnetic flux, induced current will be generated, which will try to oppose the flow of main current. Okay, when the main current is increased, the induced current opposes the current. Induced current opposes the main current, and it will be opposite in direction. Okay, this is in the first diagram given over here. Now in the second diagram, what is the difference in these two diagrams? Over here, the rheostat is at maximum value. So maximum of the resistance is involved. So when we increase the rheostat, resistance will increase. When resistance increases, current starts decreasing. Now when current starts decreasing, what happens? Again, the direction of the current still remains the same, but current is decreasing. So when there is a change in current, there will be a change in magnetic flux, and again there will be an induced current. But now, what happens when the main current is itself decreasing? When the main current is decreased, then the induced current flows in the same direction as the main current and opposes the decrease in the main current. So now induced current will start flowing in the same direction as main current, so as to let this current not go down to zero. So to add up to this main current, so it doesn't go back to zero. So what is this main current trying to do? Main current is trying to come back to zero, but induced current is not letting it do so. In the first case, the main current was trying to increase, but induced current was not letting to do so. It means induced current always opposes the main current. So this is according to Lenz's law. According to Lenz's law, the induced current so generated always opposes the main reason why the current is being generated. Now the phenomenon of electromagnetic induction, in which on changing the current in a coil, an opposing induced EMF is set up in that very coil, is called self-induction. So the process where the main current, on changing the main current, opposing current is generated. Opposing current is EMF, or this is also known as back EMF. With the main current, an induced current is generated in the same circuit. That is why it is known as self-induction. It is being induced, the current is being induced by the circuit itself. That is why it is known as self-induction. Now, thus when the current in the coil is switched on, the self-induction opposes the growth of the current, and when the current is switched off, the self-induction opposes the decay of current. This is why the self-induction is also called as inertia of electricity. So, self-current or back EMF opposes the main current. That is why it is known as inertia of electricity, which is not letting it increase also, which is not letting it stop also. That is the same thing which happens in inertia. Now we will try to find out the coefficient of self-induction. Okay, coefficient of self-induction. So let us consider a coil of n turns carrying current I. So we consider in that particular coil before there are n number of turns which is carrying I current. Okay, I current. So n number of coil will generate flux in all the turns. The current will be flowing in that coil and the flux will be generated. So now total flux in one coil is phi b. So in total n number of turn, flux will be n into phi b. So this is directly proportional to the current. It means that when we increase the current, the flux will also increase. Now if you remove this sign over here, n phi b is equals to Li. So this L is known as coefficient of self-induction. Coefficient of self-induction. Now from this equation, L is equals to n phi b by I. Remember this equation, it is important. This is your self-induction. Now, not only current will be induced, EMF will also be induced. So, with this L, let us see what will be our EMF. EMF is equals to minus n del phi b by del t. This is from Faraday's law. So now, replacing the value of n phi b over here. But if we change this n phi b over here, what do we get? Or first of all, let us write like this. N phi b divided by del t. So in place of this, we are writing this value. Minus del Li divided by del t. Now L is a constant, which is coefficient of self-induction, so it can be written out. So this becomes del I by del t. Del I by del t is change in current with time, or rate of change of current in the coil. Or from the same equation, what do we have right now? We have minus L del I by del t. So from here, what will be our L? L is equals to minus E. This will go in the denominator. So this is our coefficient of self-induction with respect to EMF. Now when the rate of change of current in the circuit is 1, del I by del t is equals to 1, then your coefficient of self-induction will be equal to the EMF. Now the unit of self-induction is Henry. Unit is Henry. This will be small h, okay? Henry, denoted by capital H. If you write the symbol, it is capital H. If you write the name, it is small n, small Henry. Henry. So 1 Henry is equals to, the self-inductance of a coil is 1 Henry when an induced EMF of 1 volt, is set up in a coil due to a current changing at the rate of 1 ampere per second. So remember the definition, which is given in the book also. Now the smaller unit of Henry will be millihenry. So 1 millihenry is equals to 10 to the power minus 3 Henry, or 1 microhenry is equals to 10 to the power minus 6 Henry. Remember this because in more of the calculation we use the smaller units rather than the larger units. Now the dimension of L, that you can find it out, okay? Dimension, you know how to find from the formula itself. You can find the dimension. So to find the dimension, use this formula, that is E by del I by del T. Use this formula to find the dimension. Now the another topic is self-inductance of a long solenoid. In today's class, I will try to cover up the topic related to self-inductance. So now the self-inductance of a long solenoid. Here is a long solenoid. The total number of turn in the long solenoid is N. Okay, N is the total turn. I will be the current. Okay, I will be the current. N is the total turn. Now small n will be number of turns per unit length. Now number of turns per unit length mean, if there is a very long solenoid, what will be the number of turn in 1 meter of that solenoid? So it will not be capital N, but it will be small n. This will be is equals to capital N divided by L, which is the L is the length of the solenoid. Okay, we'll consider A also. This is area of cross section of the solenoid. So now, according to the derivation done in the previous chapter, magnetic field due to a long solenoid is B is equals to mu naught N L. So in place of small n, we are writing capital N divided by L into L. Sorry, mu naught N I, okay, not L. So this will be I. Now mu naught is permeability of free space or permeability constant. Next, to find the flux, you have to find the self-inductance, you have to find the flux. Flux is equals to, magnetic flux in each turn will be B into A, magnetic field into area of cross section. So we can find the how many number of, if suppose there is this ring over here, the area of this ring is A, the number of fill lines coming from this will be B. So when we multiply this, we are getting the total number of flux, which is number of magnetic fill lines passing through a certain area. Now this is for 1 turn of a solenoid. Now for n turn of a solenoid, we will also have to find that. So before that, let us first put the value of B over here. This becomes mu naught N by L I into A. So second, what I told you, this is only for the 1 turn. So suppose for n number of turn of a solenoid, for n number of turn of a solenoid, we have to multiply n with the flux phi B, which is equals to, multiply this with n. So ultimately what we get is, we get n phi B is equals to mu naught n square I A by L. Now the self-inductance of a solenoid is, therefore, we know that previously we have done this, L is equals to n phi B by I. Just before this we did a topic. In that I have told you what will be the L. So from there only I am just writing the equation of L from the previous topic. So now the value of n phi b will put over here. So mu naught n square IA divided by L divided by I gets cancelled. So L is equals to mu naught n square A by IA by, okay, I'm so sorry, I got cancelled. So mu naught n square A by L. Now the unit of L is Henry. It is clear from this equation that we may take the unit of mu naught as Henry, the unit of this mu naught as Henry per meter square or joule per ampere square. If the solenoid would be wound on a core of constant permeability, suppose right now whatever I have drawn over here is a solenoid, in between nothing is there, but if you put any material like a soft iron core, then it has got a permeability, okay, not the absolute permeability or the permeability of free space, but we have mu, that is constant permeability, which depends upon the core material. So if you replace this over here, then this becomes L is equals to mu n square A by L. This is when inside the solenoid we have a material instead of free space. Okay, so this is the equation for self-inductance of a long solenoid. Now in the self-inductance part also there is one topic is there, that is some examples of effect of self-induced current that you go through by yourselves. Okay, so this much for today. In the next class I'll discuss about mutual inductance.